A pillbug in your garden grows to maybe 2 centimeters. Its deep-sea cousin grows to 50 centimeters. That's not a typo, that's a 25-fold increase, the equivalent of a house cat growing to the size of a horse. Why the deep ocean makes everything giant is one of the strangest phenomena in biology. Down in the crushing darkness, where no sunlight reaches and temperatures hover just above freezing, creatures grow to sizes that seem physically impossible. Squids with eyes the size of dinner plates, crabs with legs spanning 12 feet, sharks that don't reach adulthood until they're 150 years old, worms that stretch longer than a blue whale. Scientists have been trying to explain this for over a century, and they've discovered that the deep sea breaks every rule we thought we understood about how big animals can get. The phenomenon is called deep sea gigantism, or sometimes abyssal gigantism, and it affects everything from crustaceans to cephalopods to fish to jellyfish. But understanding why requires you to understand what the deep ocean actually is. Below 200 meters, sunlight starts to fade. By 600 meters, it disappears completely. You're in permanent darkness. Temperatures drop to around 4 degrees Celsius. That's 39 degrees Fahrenheit. And pressure increases by 1 atmosphere for every 10 meters you descend. At 1,000 meters, you're experiencing 100 times the pressure at sea level. At 4,000 meters, the average depth of the ocean floor, it's 400 times. You'd think this would crush life into smaller, more compact forms. Less surface area, less vulnerability, the opposite happens. Not to worry though, it gets weirder. The most dramatic example is the giant isopod. If you've ever seen a pillbug roll into a ball in your garden, you've met the giant isopod's tiny cousin. Regular isopods, the kind you find under rocks and logs, max out at about 5 centimeters. Most are smaller than your thumbnail. The deep sea version, the largest confirmed specimen of Bathynomus giganteus, reached 50 centimeters. That's 20 inches, the size of a small dog. One report claimed a specimen of 76 centimeters, though scientists haven't verified that measurement. Giant isopods live at depths from 550 to 2,100 meters. They have compound eyes with nearly 4,000 individual facets designed to capture whatever faint traces of bioluminescent light exist at those depths. Their eyes contain a reflective layer called a tapetum that doubles the available light, similar to what cats have. In total darkness, they can still see. They're scavengers, feeding on whale carcasses and dead fish that drift down from above. When a whale dies and sinks to the ocean floor, it's called a whale fall. Giant isopods can detect these from remarkable distances. They crawl toward the carcass and feed. And here's the part that sounds impossible. One giant isopod in a Japanese aquarium survived for 5 years without eating a single meal. 5 years, no food, just existing. That's only possible because of how the deep ocean changes metabolism. Cold temperatures slow everything down. Chemical reactions happen more slowly. Energy demands drop. These creatures don't need much fuel because they barely move. They can go years between meals and still survive. Some researchers believe giant isopods gorge themselves so completely when food is available that they can barely move afterward. Then they digest that meal for months or even years. In case you needed more proof that size works differently down there, consider the colossal squid. Most squid species you'd encounter measure around 1/2 meter, 1.5 feet. The kind served as calamari. The colossal squid, Mesonychoteuthis hamiltoni, reaches 14 meters when you include the tentacles. Its body alone, the mantle, can weigh 500 kilograms. That's over 1,100 pounds. The heaviest specimen ever captured weighed 495 kilograms, and scientists believe larger individuals exist based on beaks found in sperm whale stomachs. And unlike most squid, which have suckers on their tentacles with small teeth, the colossal squid has something different. Rotating hooks, sharp, swiveling hooks attached to both its arms and tentacles. Some of these hooks can rotate 360 degrees. They're designed to grab prey and never let go. Once those hooks sink in, escape becomes nearly impossible. Its eyes are the largest of any animal that has ever existed. Not just living animals, any animal in Earth's history, up to 40 centimeters across. That's 16 inches, bigger than a basketball, bigger than a dinner plate. These massive eyes evolved for one specific purpose, to spot the bioluminescent trails of sperm whales hunting in the darkness. The colossal squid can detect predator movement from over 120 meters away. That's longer than a football field. Shockingly, despite its massive size, the colossal squid barely moves. It's not a pursuit predator like its smaller cousins. Scientists estimate it only needs about 30 grams of food per day. That's roughly 1 ounce. Imagine a 1,000-pound animal surviving on an ounce of food daily. It's an ambush predator that conserves energy by floating motionless in the darkness and waiting for prey to come to it. When something swims close enough, those hooked tentacles strike. Sperm whales are the colossal squid's main predator. These whales dive to depths of 2,000 meters or more to hunt. And when these two giants clash, neither escapes unscathed. Most adult sperm whales are covered in circular scars from colossal squid hooks. Some whales have hundreds of these marks. The battles happen too deep for humans to witness, but the evidence is written permanently on the whale's skin. But here's what makes it worse. The colossal squid isn't even the largest creature living in the deep. The Japanese spider crab holds the record for the largest living arthropod on Earth. Its leg span reaches 3.7 meters. That's over 12 feet from claw to claw. Longer than most cars are wide, longer than many bedrooms. Its body, the carapace, measures about 40 centimeters across. But those legs extend outward in every direction, like a living nightmare. For comparison, the largest land arthropods today are coconut crabs, which reach about 1 meter across. The Japanese spider crab is nearly 4 times wider. It can weigh up to 19 kilograms. That's 42 pounds of crab, and it can live for up to 100 years. Talk about slow and steady winning the race. These crabs live at depths between 150 and 600 meters off the coast of Japan, particularly in Suruga Bay. Despite their terrifying appearance, they're actually gentle scavengers. They move slowly across the seafloor on those impossibly long legs, picking at dead organisms and algae. The enormous legs aren't for speed or combat, they're for stability on the uneven ocean bottom and for reaching food in crevices other scavengers can't access. So why do deep-sea creatures grow so large? Scientists have proposed several explanations, and the answer appears to be all of them working together. The first is called Kleiber's rule. Larger animals are more metabolically efficient than smaller ones. A mouse burns energy at a much higher rate relative to its body weight than an elephant does. This comes down to surface area versus volume. Smaller animals have more surface area relative to their volume, so they lose heat faster and need to replace that energy constantly. In the deep sea, where food is scarce and energy conservation is everything, being bigger means you waste less energy simply existing. You can survive longer between meals. The second is Bergmann's rule. Animals in colder environments tend to grow larger than their warm water relatives. Cold water slows metabolism, which means organisms grow more slowly, but for much longer periods. They don't hit maturity quickly and stop. They keep growing for decades. The Greenland shark is the perfect example. This species doesn't reach sexual maturity until it's approximately 150 years old, a century and a half before it can reproduce. By the time it stops growing, it's reached 7 meters in length. That's 23 feet. Some individuals may live over 500 years. The oldest confirmed specimen was estimated between 272 and 512 years old. You couldn't encounter one of these sharks and know how old it was just by looking. The oldest Greenland sharks alive today were swimming before Shakespeare was born, before Columbus reached America, before the printing press was invented. The third explanation is the oxygen temperature hypothesis. Cold water holds more dissolved oxygen than warm water. It's simple chemistry. And deep-sea creatures have extremely slow metabolisms, meaning they use oxygen very slowly. This creates a situation where oxygen supply far exceeds demand. The creature can get all the oxygen it needs even with a very large body. Without oxygen limitation, there's no ceiling on how large these animals can grow. Unfortunately, for scientists trying to find a simple answer, none of these rules explain everything on their own. The deep sea is still largely unexplored. Only about 5% of the ocean floor has been mapped in high resolution. New giant species are discovered regularly. Every expedition seems to find something larger than expected. In 2022, researchers discovered a sea sponge the size of a minivan in deep Pacific waters. Tube worms at hydrothermal vents grow to 2.7 meters. King of herrings oarfish reach 11 meters in length. That's 36 feet. And the lion's mane jellyfish has tentacles that can extend 36 meters. Longer than a blue whale. All of these dwarf their shallow water relatives. The pattern holds across almost every taxonomic group: crustaceans, cephalopods, cnidarians, fish, worms, echinoderms. Whatever family you examine, the deep sea members are dramatically larger than their shallow water cousins. There's another factor that researchers often overlook: fewer predators. At 2,000 meters depth, there aren't many animals capable of eating a 50-centimeter isopod protected by a thick exoskeleton. Its shell is dense. There's very little meat inside relative to the effort required to break through. Most predators simply don't bother. The giant isopod has survived for over 300 million years using this strategy. It's been around since before the dinosaurs. When there's nothing hunting you, there's no evolutionary pressure to stay small and fast. You can grow slowly, conserve energy, wait decades between meals, and eventually reach sizes that would make you easy prey in any other environment. In the deep sea, size is protection. But here's the concerning part. Deep sea gigantism may be disappearing. Climate change is warming the ocean from the surface down. Warmer water holds less dissolved oxygen, and as surface temperatures rise, the cold oxygen-rich water that normally circulates down to the deep ocean is becoming warmer and less oxygenated. The conveyor belt that refreshes the deep sea is slowing. Researchers at the University of Hawaii have warned that the stable, cold environment these giants depend on may not remain stable. Animals that evolved for conditions that haven't changed in millions of years may not be able to adapt to changes happening in decades. The giant isopod, the colossal squid, the Japanese spider crab, the Greenland shark. All of them evolved in an environment where the fundamental rules have stayed constant since before dinosaurs walked the earth. If those rules change, these animals have nowhere to go. There is no deeper ocean. There is no colder water. The deep sea is the end of the line. Surprisingly, we've already seen this play out in the fossil record. During the Paleocene-Eocene thermal maximum, 56 million years ago, ocean temperatures spiked dramatically due to volcanic activity and methane release. Deep-sea gigantism declined. Many large deep-sea species went extinct. It took millions of years for ocean conditions to stabilize and for giant species to recover. We might be recreating that extinction event now, just faster, much faster. What makes deep-sea gigantism so remarkable isn't just the size of these animals, it's what they represent: an alternative set of rules for life. A parallel world where cold and darkness and pressure don't limit growth, they enable it. Where being slow and huge beats being fast and small. Where a pill bug can grow to the size of a football. Where a squid can have eyes larger than any dinosaur that ever lived. Where a crab's legs can stretch across the width of your living room. That's the reality of the deep ocean, where everything grows giant. Because in the darkness and the cold and the crushing pressure, size isn't a weakness. It's the ultimate key to survival.